Hello everyone, my name is Jacoby Bussey and I'm one of the TAs for Econ 210. And today we'll be going over problem set 4, question number 2, the golden rule. Okay, so we are asked to consider the Solow model that we analyzed in class, which had investment share S, reaching ratio rate delta, and a population growth rate N, and a production function YT is equal to A, KTA, LT, A, 1 minus A. Basically, this typical Solow model we've already seen. Okay, and we were asked to find an expression for the steady state level of consumption per person, C star, in terms of the model parameters only. Okay, so what does that mean, right? So basically, our goal is to figure out what C star is, right? So C star is just this. It's just consumption at time t, labor at time t. This is because, as we already know in the Solow model, we presume that everyone works, and so we can divide everything by labor. Okay, so, well, that's great, but what is consumption, right? So we actually have an equation for consumption that we can use here. If we're going to find C star, which is the steady state value of consumption in the Solow model, right? We're going to need to first understand what consumption is. Okay, what's consumption? Consumption at time t is just equal to 1 minus S YT, right? So S in this case is the savings rate. And so the savings rate is basically how much money, rather how many cookies we save to invest in more capital, right? So if we're not investing those cookies, we're eating those cookies, right? We're consuming them. So that's why we have 1 minus S. And so luckily, right? So this is CT flat, right? Okay. So if we want to find C star, right? If we want to find capital consumption per capita, we need to divide everything by L. Okay. So this just equals CT. This is consumption per capita. And this is the same thing as IT divided by LT, which we already know is just output per capita. Okay, well, that makes things easier for us. So what's our equation for output per capita? Well, this is another good thing you should kind of keep in mind when you're working Solow model. It's just this. YT is equal to A, K, T, A. There's a very simple derivation for this, where we basically divide the entire our output equation by L. And then from there, it turns out that all of the KTs and the LTs kind of go together. And so that we find is this. This is one of the things we talk about when we think of AK models. In any case, we know that YT is just equal to this equation, right? So if that's the case, then we can just plug in our LT or YT equation right here in for this YT. Let's do that. So now CT is equal to 1 minus S times AKT to the A. Okay, so now we've done this. And so remember, we're thinking about in terms of C star, right? And so that's important. We're thinking about in terms of what is consumption at the steady state. Well, if we look at our equation here, we have 1 minus S, exogenous variable. A is an exogenous variable. Alpha is an exogenous variable. KT is determined within our model. Okay. And so if we want to figure out what CT is going to be, consumption per capita is in the future, what we really need to do is figure out what is capital per capita in the future, right? So if we figure out what everything is in the future, then we know what this consumption per capita is going to be in the future. Okay, so if you already know that these are constants, these don't change, then we need to figure out what capital per capita is in the future. Luckily, we already know that, don't we? That is just a steady state of per capita capital. So we know that in the long run, in the steady state, it's just gonna be this. Right, and so what we can do here is we just have this. Okay. Okay, if this is true, if we know that in the future, KT star is going to be, well, K star is going to be SA divided by N plus D raised to the 1 minus A. Well, that means we can just plug this in for KT because we're trying to figure out what CT is in the future, what consumption per capita is in the future, and we know what capital per capita is going to be in the future. So we can just plug that in and we know exactly what consumption per capita is going to be in the future. Let's plug that in. So now C star is going to be 1 minus S A, and this is K star A, and this is just equal to A divided by N plus D, and this is raised to A, 1 minus A. And notice these are all exogenous parameters, which satisfies our question for A. Okay. So on this question, view the steady state level of consumption per cap, but rather per person, as a function of the investment share. Okay. Let S goal be the value of the investment share that maximizes the steady state level of consumption, subject C star S, subject to the fact that the savings rate is in between 0 and 1. It's called the golden rule of investment share. Find the expression for S goal in terms of the other model parameters. Okay. So what does that all mean? That just means that C star, we recognize that C star is just a function of the savings rate, right? So it means that savings rate is a variable in this model right here, right? So we can see that right here. S is right here. We have S right here, right? So now what it wants us to do is try to maximize the steady state level of consumption, C star. Well, how do we maximize a variable? Well, if we remember from calculus, if we want to maximize a variable by another variable, right? Well, what we do is we just do the first derivative, right? And we solve it for 0. If we solve that for 0, then we find what value, in this case, S should be such that it would maximize consumption. This will be our S gold. And so let's try doing that. So first, let's break this up a little bit. So 1 minus S A, S A, N plus D, A 1 minus A is the exact same thing as A times S A, N plus D, A 1 minus A minus S A, S A. N plus D, A 1 minus A. Okay. So we need to take the derivative of this, right? We can make it a little easier on ourselves if we just split, if we take the S's out of this kind of jumbled expression here and here. Let's do that. So this is just the same thing as A plus D times S A to the 1 minus A, right? One minus A And just like the other one, this is the same thing as s times s a to the 1 minus a n plus d to the 1 minus a. So why is this true, right? Well, if we had the square root of something, let's say we had the square root of 4, that's the same thing as the square root of 2 times the square root of 2. And 4 is the same thing as 2 times 2. So basically, following this principle, we can take our functions outside of these exponents. So quick review there. Just want to make sure the math was clear. Okay. So now we've done this. Now we want to take the derivative of this. Before we do that, we want to combine this together, right? So this is just 1 minus a, so that means this is the same thing as, there's like a invisible 1 here, so we can just add these together. So we have s 1 minus a, 1 minus a, plus a, 1 minus a. And this is the same thing as plus b, a, 1 minus a, s, a, 1 minus a. How that is this. Right, so if we add these together, we just get s 1 over 1 minus a, right? Times a over n plus d, a to the 1 minus a. Okay. S of a, 1 minus a n plus d, a 1 minus a. Perfect. Okay, so now let's take the derivative of this. So we're just going to use our rules. And so from here, we're trying to, this is c star. So derivative of c star in terms of s is just a 1 minus a, because we're doing the power rule. A n plus d, and then we're going to have a 1 minus a here, and then we have s. And so remember, we're subtracting 1, so this is the same thing as a 1 minus a minus 1 minus a 1 minus a, right? Okay. And this is all being subtracted by s, rather, we'll take derivative of this part too. So now we have 1 minus a and then now we have s 1 minus a minus 1 minus a times a divided by n plus d, a 1 minus a. And this is all equal to 0. So first things first, we have a lot of terms here, right? It would be a lot easier for us if we could just get rid of all these a divided by a's and stuff like that, like all this stuff right here, right? That's the first thing. And notice we can actually do that. So we can combine like terms here. Notice that this the same as this over here, right? So that's the first thing we can do. We can say A over n plus D, A 1 minus A. Now we have over here, A 1 minus A. And now this is just S A 1 minus A minus 1 minus A plus A, right? In this part, just 1 minus A, S, and then we have, again, our parentheses, 1 minus A minus 1. There we go. Okay. This is all equal to 0. Well, if that's the case, we can just divide everything by this. If we divide this on both sides, then that means we'll have 0 on the right side, and we'll also have 0 on the right side, and we'll get rid of that on the left side, making our jobs a lot easier. So now if we divide this on both sides, we should just get A 1 minus A S A plus A minus A. Now we have 1 minus A S 1 minus A 1 minus A 1 minus A, and this is equal to 0. Okay. So now let's also work with these things in the exponents. And so from here we see that we should have a 1 minus A S, and from here we can just distribute this minus sign, and so now we have a minus 1, but we have plus 2A, right? So we have 2A minus 1 minus A minus 1 minus A. And so now from here we have distribute the negative again, and so now we have 0, right? So 1 minus 1, and but we also have a positive A. So A, 1 minus A. Okay. Now what's next? So from here, notice we can combine like terms again, because we have a 1 minus A in the denominator of both of these terms. So if we multiply both sides by 1 minus A, right, then we can distribute that 1 minus A to both, and so from there, 1 minus A times 0 is still 0, so we should get this. We multiply by 1 over 1 minus A, we should get this. A S to, this is being raised to A minus 1 minus A minus 1 minus A S A to the 1 minus 1 minus A. And this is all still equal to 0. Okay. A lot of computations, but we're almost there. Okay, so now, oh, rather, you gotta make sure we multiply on both. So now this is just 1. Right, this is everything. Okay. So now what we're gonna do is we're gonna add S to both sides. I mean, SA to the 1 minus A on both sides. So now we just have this. Perfect. And so now this is a lot easier for us to work with. And so now we're trying to solve for S, right? Or S gold. And so if we raise both sides to the 1 minus A, or rather what we can do instead, we can actually divide both sides by S to A minus 1 and 1 minus A. And so it's gonna be a little funky, but we're gonna do this because we can utilize those properties and subtract things out. So remember from algebra, so I guess think of this. This is the same thing as SA minus A minus 2A 1 minus A. It's the same thing as that. And so from here, what we can do is we can distribute that negative. And so now we have SA minus 2A plus 1 all over 1 minus A, which is equal to, and we can just subtract our minus 2. And so now we have 1 minus A, 1 minus A. So now we have A equal to S, 1 minus A, 1 minus A. And now finally, look, this is just A with S, right? Because this is equal to 1. So we figured out that the golden rule for the investment share, if we want to maximize consumption, is that we set our, is when we set our savings rate equal to A. Okay. So now we figured out the golden rule. So now we're looking at C, and this is one of our situations. Starting with the steady state, S is greater than S gold, right? Which means that it's not being maximized in the future. Suppose the investment share is permanently reduced to S gold. Use the phase diagram to show what happens to capital per person as a result of this change. What is the time path of consumption per capita before and after the change? Okay, so it's important to note that when we're working on this, what we've done here is we've shown that there's a point where we've maximized this function, right? So the idea here is, it may not look exactly like this, but the idea is there's some point in the savings rate. This is A, S, this is consumption, where we've maximized consumption, right? And so if we are saving less than this point, let's say right here, then that means we're not consuming as much as we could. Rather, yeah, we're not consuming as much as we could, which is kind of unintuitive, right? Because we're saving less. So you think, okay, if I'm saving less, I should be consuming more. But in the long run, right, when you'll have more things to consume in the future if you're willing to stave it off for now. If we are over here, right, if we're saving a lot, then we're obviously going to consume a lot less in the now, not here and now. Okay, let's draw what happens in SOLO, right? So drawing our diagram here. Remember, we have KT, and we have KT plus 1. Okay, this is our 45-degree line. And then what we're going to have is our equation here. This is our steady state. And so we already found out what the steady state is going to be. It's K star. We'll presume that we're at our steady state before we make the change. And so we are and so remember the equation for the fundamental equation for the SOLO model is like this. SKT A plus 1 minus D plus N KT. Okay. So the question said that we're starting from S greater than S gold, right? And then we go down to S gold. So what does that mean, right? That means S is going down. Savings rate is going down. So if savings rate going down, look at our equations here. S is in the numerator here. That means if S goes down, this equation also goes down. Let's redraw this. Okay, so now we know this is going to be our new steady state. We know that over time, capital per capita is going to go down. Let's write down the new equation as gold. A 1 plus N KTA STM. And so we also knew that KT doesn't jump, and this is an important distinction too. KT doesn't jump because this particular exogenous variable has nothing to do with capital per capita in terms of how it's defined. So basically what I mean by that is KT does not jump because this is capital per capita. Because the capital share didn't jump at this particular time, and also people didn't jump at this particular time. So nothing jumps, it's just a smooth ride down, right? And so when we're looking at this, we should note that, oh, okay, look, we were here and now we're below the 45-degree line, so we're going to go to the left. So go to the left here. So if we draw a line here, there you go. Now we are all the way back at our new steady state. So what does that mean? Let's draw our time diagram to see what happens to KT. So at time t0, we're here, right? And then we implement the new policy. At time t0, we implement the policy, boom. We are now going to reduce our savings rate to this. And then this is KT star. This is where we are initially. Okay. And so looking at our graph here, we see that, okay, we're going down, right? So we're going to smoothly go down. Perfect. Okay. We're going to smoothly go down until we reach this new steady state KT star. Okay. So now what's next? We are interested in what happens to consumption, right? And this is where it's very important to always write down the equation of the variable of interest, right? So, for example, in this case, our variable of interest and that we're working on in terms of drawing our time path for is consumption, right? The consumption per capita equation is just this, right? If we go back up, after all the work we did, it's just this. One minus S, A, K to the A. So let's just write that down. 1 minus S, A, K to the A. Right? Okay. So notice our variables, right? Whenever we're trying to think of like a direct effect, we need to think of, do any of our variables change? And notice at time 0, right? At C times 0, our S changes, right? We go from our high S, a high savings rate above S gold, to S gold. So we're going down, right? And so because we're doing 1 minus S, if we are going downward, then that means the value for consumption goes upward because it's a subtraction. Okay. So from here, what we're going to do is, so this is going to go up because this goes down. So if we draw our time chart, we should see that over time, that rather at time 0, t0, we should see a jump. because this is going down initially, right? It's especially in our equation. The direct effect is that the savings rate is going down, right? And so that means that our consumption times T0 goes up. So if that's going up, now we have this. Okay, then what happens next? Right, and this is where it kind of gets interesting. So first off, we know that by definition of the savings rate, by the definition of the S gold, we know that our steady state for consumption should be greater than it was previously, because we started at some point that was not the steady state. Then we moved to a point that is, rather, we started at some point that was not at S gold, and we've moved to S gold. Therefore, because we know that this is the point that maximizes our consumption function, right? Therefore, this point that we started out must not consume as much as the point that we reach to next, right? And so if we look at our function again here, so rather, if we look at our we're looking at our timesheet right here, time card. We see that, rather, our time path. We see that we should end at a consumption that is higher than where we started. Right? We should end with a consumption that's higher than CT, so our initial steady state. Okay, but how much higher is the question, right? So should it be even higher than our jump, right? We made a little jump here. Should it be even higher than our jump, or should it be below our jump? Okay, that's a good question. And this is where we kind of have to think about what happens over time. So looking at our equation here, we see that after that little initial pop, right, these variables don't change anymore, right? Our 1 minus S and A, they do not change anymore. And so the only thing that changes after that is our KT. And so after T0, KT goes down, right? So if KT goes down, look at this, CT must go down, right? If per capita capital goes down, that means per capita consumption must go down. So they're both, so if this is going down, as we see in this one, we should also see the exact same shape over here. So we know that instead of there being a jump and then it continue going even higher than that, we know that it must go down because of the fact that capital per capita goes down. Okay, this is our new steady state, which by definition is higher than the one that we started at. Okay, so time for consumption per capita. Okay, so that's basically the word explanation. We initially started at a certain savings rate, and then by definition, we know that we're going to a higher one later on, right? We're going to a higher consumption in the future, right? In their new steady state. Then from there, we have to think about the direct effect. The initial direct effect is that our savings went downward. So that means we should see at time 0 an initial jump in consumption, right? Because we've increased how much we're going to consume. But because of the effects of that, our capital goes down, right? And so as it's going to this new steady state that's below for capital, it's also going to a new steady state that's below for consumption. And so over time, it's going to go reach to a higher steady state than we initially had, but it's still going down. Okay. Now we're thinking about D. So if households prefer more consumption to less, would they prefer to live in an economy where the savings rate is greater than S gold, right? Use your answer from part C to explain. Okay. So what does it mean to live in an economy where the savings rate is greater than S gold? Well, that means we are 100% going to be consuming less than we would be if we were at S gold, right? So notice, this CT is below our consumption right here, and this right here is below our new CT star, right? Our new consumption per capita double star, right? So we know that in the future we would be consuming less if we stayed at this point, if we stayed as we were in this economy. Even worse, even in the present state, we were consuming less than we could as well, because we could just reduce our savings rate even below this point too, and we'd still be consuming more than we are right now, right? So the way this problem wants you to think is in terms of two different time periods, the future and now. Okay, so in the future, we know that we're obviously consuming less because we are below the S gold. So obviously we know we're below that S gold, we are going to consume less in the future for a fact. But now now we're looking at the present. But okay, maybe the present's better, but it's not, because we are still consuming less than we would, because remember, it's 1 minus S. We have a very high value of S right now. Our savings rate is high. So if we're saving a lot, right, we're saving more than we would at S gold, well, that means we're saving a lot. And if we're saving a lot, that means even right now, we could be consuming more, right? So too high savings in time two. So here's the situation. Right now, we are consuming less than we could, and in the future, we're consuming less than we could. So why would we ever want to be in this economy if our goal is to consume? We wouldn't. So this is a bad situation. We don't want to be in this one. Okay. So they would never prefer to live in this economy. Okay. And the next question asks, what about a situation where S is less than S gold, right? Okay. Well, that's a little different, right? Because remember, in this first part, we were talking about how right now we're saving too much. In the future is below S gold, so in the future we're also still not consuming as much as we could. So right now we're not consuming that much, and in the future we're not consuming that much. But if S is less than S gold, right now we would be consuming more, right? So so right now, right, if we have a small s, right, if we're looking at our equation here, at time t0, small values of s mean a greater ct, right? So as s increases, consumption goes down at time t0, right? Right now, if we just look at time right now, if you save more right now, then you consume less, right? So at time t0, we're consuming more, right? We're consuming more than we would if we are at S gold right now. But in the future, right, we would be consuming more at S gold than we would be if we were consuming as we would at our S, which is below S gold. That's unintuitive. How does that work? Remember, we drew this. And we're thinking about in the long term, right? And this is S gold makes sense at the steady state in the long term. If we're thinking in terms of one step, if we're thinking like right now, well, yeah, right now, it would be better for us to be interested in a very low savings rate, because we're at a low savings rate, then we'll consume more right now. And that's the real distinction here. So let's draw some to illustrate what we're talking about. Okay. So if S is less than S gold, then what we could do is increase our savings rate such that it reaches S gold, right? Let's say we did that. Okay, so here's A plus N AT. And then this is, that's right. Yep, plus 1 minus D. Plus N KT, right? And this is our 45-degree line. If we increase our savings rate to reach our new S gold, right? S gold. Okay, T. Well, then from there, we go up here. And look, we're cruising up towards a new point, right? Our new steady state, where capital is higher. Okay, so if we draw the time paths for capital, at time t0, we institute a new policy. We're going to save more to reach our new proper savings rate. We go like this, right? Because there's no jumps in capital per capita. We're just sliding over to this new point. So now we have, start with this, now we're going to this. Okay. Perfect. And so another question is, what does consumption look like? Okay, let's write down our equation. Every time we want to draw a time series diagram, it's always a good idea to write down our equation. Don't over to read that with me. That's fine. Okay. So CT is just equal to 1 minus S, A, S, A, K, A, K, T, A. Okay. So if the savings rate is going down, right? Wait, it's on the page. Savings rate is going down. I mean, rather going up, what happens? Well, at time t0, right? This savings rate has gone up. This S is negative. It is hurting our value of CT0 at t0. So that means it's going to bring it down. So this is going up, this is going down. That's our initial direct effect. Okay, so start at t0, we are going down. Okay, now what? Okay, but now we know, look at our KT, it's going up, right? It's going up. So that means this has to go up because over time, these variables don't change because we're now at S gold. And the only thing that changes now is just KT. And so KT is going up. So if KT is going up, that means that this function is also going to increase too. So, okay, so now it's going up. The question is, how high should it increase? Should it increase higher than where we started, or lower than what we started, right? So should it increase just to here, or should it increase all the way above? Well, the answer is in our definition of the steady state, rather, in a definition of S gold. We defined S gold as the value for S by which we maximize consumption in the future, right? So if this was higher, if this was less than S gold, if this was less than C star, well, that would mean that that means we would be consuming less than we would at the maximum. We already defined the maximum as S gold. So that means it's impossible for us to be consuming less than we would be in the future. So that means this is going to be this. We're going to go up above. So we start at initial T0, instead we're going up to this new C star, which is above. Okay, so why is this important? So if you're a household in this economy where S is less than S gold, our economists tell you we are less than S gold, we should definitely increase our things we consume more. Remember, your goal, because we are in this consumer economy, our goal is that I just want to consume, consume, consume. If I care more about the present day right now than I do in the future, well, I might just be very happy with where I am, right? I might be very happy with the fact that, well, in the current term, I'm consuming way more than I would if I went to S gold right now, right? So see this jump. Remember, this dip happens, right? This dip happens if we go down, right? If we increase our savings rate. So if I'm interested in consuming, I may want to prefer just to stay where I am. S gold may not be that good for me because I know that's going to happen in the future. I may be dead in the future. I don't really care about what's happening in the future if I'm going to be dead. So I'm just going to consume what I am right now. However, if I'm interested in the future, then S gold is better, right? In that case, then I wouldn't really want to be here because, like, well, I know what I'm consuming. I know I'm going to lose some stuff now, but in the future, we'll be consuming crazy cookies, a crazy number of cookies. So I'm going to actually prefer to be in this state, right? The state where we're at S gold. And so the idea here is this is more of a maybe because it depends on your perceptions, rather how you value time. So if you prefer the present as opposed to the future, then maybe you would prefer to be in this economy where S is less than S gold. However, if you value the future, right? If you value the future over the past, then you're gonna think, well, I'm going to be consuming even crazier cookies if I would wait some time. So I actually would not want to be in this economy. We should just pump it up to S gold right now. And that's the idea. And that's how you work on problem set 4, question number 2. Thank you so much.